Okay. So this is our last week. Some of us are just realizing this. This is week 10. So last week of the quarter. Exams are next week. So you got an extra 2 hours to do your PA5 because I just now downloaded from Git. So I got it in a few minutes late. I still got it. So I will get those graded. It's probably not going to happen today, but sometime in the next day or two, I will hopefully get through those. Looks like I have 25 of them to grade. So SLP presentations are tomorrow. Again, we're not doing them in the digital lounge at 3, so we're going to do them in class. Okay? So make sure you come to class, right? And I'll have each person or a group of people come up and just basically do a few-minute presentation as if you were at the expo and somebody said, hey, tell me about your project, right? So very informal, just kind of talk to us, tell us what you're doing, and so on. And yeah.
Do you have an HDMI cable?
I do. What do you want on the other end, HDMI?
I have a USB Type-C.
I do not.
I have a USB Type-C to USB 2 converter, but I don't have.
But that's your only output port is USB-C?
Yeah.
Okay, so there's a few things. You have like a, what do you need to show from there? You running software, or are you doing like a...
Yeah, I have IntelliJ.
Okay. My IntelliJ setup is not very good. So that's probably not going to work. So worst case, right, we can use the dock camera. It's kind of low ball, but it does work in a pinch. But if somebody, go ahead and throw a note on Discord and just ask if anybody has whatever kind of converter you need and see if someone can bring one in. That would probably be the best. All right, so extra credit will be in the form of attending class when people are presenting. And there was a big, long, wordy thing I posted the other day, but basically if we have 2 days of presentations, come to both days, you get your extra credit. If you only come to 1 day, you get half the extra credit. So that's all written up on Canvas. All right, any other questions? All right, so let's talk more about heaps. We'll finish that up today and probably talk about Radix sorting. Tomorrow will be SLPs. For this section, we might get through in 1 day. It might take 2 days. We'll see.
Can we come to both sections and get more extra credit?
You have to come to both to get full extra credit.
Oh, okay.
Yeah.
I thought you were talking about like if we had multiple days of presentation.
So if we have 2 days of presentations, then you have to come to both days for the whole class to get the full extra credit, which was 10 points.
Right. But if you come to both this section and next section.
No, you can't get extra. But you're welcome to.
Okay. Can you present twice and get extra credit?
No, but you can get extra practice.
Okay.
All right, so heaps. Let's play with min heaps. And remember, the basic setup with a heap is if it's a min heap, the smallest thing is sitting at the top. All right, so there's a good min heap. And the only thing we can say is that the root at each point in this heap is smaller than both of its children. Okay, but there's no left-right relationship. So there's the question of how to build a heap. If you have a set of numbers, how do you construct a heap out of them? And the most direct way to do that is just keep doing the insert operation. So you can start with an empty heap and do what we did on the board last week. Take your first number and make that the root. Take your second number put that in the last location on the lowest row, and then up heap, and so on. But it turns out there's a better way to build heaps. So that's going to be an order n log n process, because inserting into a heap is a log n operation, and if you have to insert n things into the heap, that's n log n. We can actually do better than that. And so this is something called heapifying. So let's just take a set of numbers. And here's how we're going to turn this into a heap. First, we're just going to put these numbers down in order in a heap without any regard to the heap property. Question? Okay. All right, so we'll just start off and we'll put these in the order in which these numbers come to us. And it's certainly not a min heap, right? Because unless your numbers happen to be sorted to begin with. Okay, so what we're going to do is we're going to start from the lowest level, rightmost position, and we're going to down heap from each node. Okay, well, everything on this lowest level has no children, so there's no down heaping to do. Okay, so this is fine, this is fine, this is fine, this is fine. We get to the next level up, now we actually have to do some work. So we'll say, is 5 smaller than both of its children? It's not, so we'll swap with the 3. And 5 has no children, so we're done. We go to the 10, is 10 smaller than both of its children? Yes, it is, so that's done. Now we go to the top level, is 20 smaller than both of its children? No. So swap with the smallest child, put the 20 here, and then repeat, is 20 smaller than both children? No. Swap with the smallest child, and 20 has no children, so we stop, and we're done. We've got a heap, and it took very little work. And you can show that this is actually order n, which is really magical. So to turn n numbers into a heap takes you on the order of n operations. And at first glance, it still looks like n log n because, you know, as this thing gets bigger, the things up here, well, we might have to do log n operations to down heap, right? But the reality is, half of our stuff in our tree, we don't have to do any work on because it's sitting at the lowest level. So that takes no work. And a quarter of the stuff in our tree, we don't have to do log n operations to down heap, we have to do one operation at most. And so 3/4 of our data, 3/4 of n, we're doing either no work or we're doing a single operation. So it's an interesting analysis to actually work out the series for this. As n gets larger, you end up basically adding reciprocals of powers of 2. And the fact that that converges gets you to this order n. And that's, I believe, a worst case. I think it's actually slightly better than that. So heapifying is a handy way if you're just starting with a bunch of data and you don't have anything in your heap yet. It's a nice way to build a heap. So again, write everything down into the shape of a heap, just in the order the data happens to be. Start from the lowest level, rightmost position, work your way backwards and down heap at each point. And that turns it into a heap. Questions about that? All right, so let's talk about implementing. So we know how to implement binary trees, right? We can do that with struct nodes with pointers to children. But with a heap, we need to move up and down, right? Depending on whether we're inserting or deleting, whether we're up heaping or down heaping. So it would seem like we need at least back pointers so we can tell who our parent is, as well as who our children are. But it turns out there's a much easier way to build heaps in a computer. So let me draw a picture. There's a 15 element tree. Let's go back to our very first data structure, which was an array. And let me store the nodes of my heap into this array, but I'm not going to use element 0. I'm going to start from element 1. So pick a node, D for example. Its index is 4. Its children are H and I. What are the indexes of H and I? 8 and 9. Okay, pick a different node like F. Its index is 6. Its children are L and M. L and M have indexes 12 and 13. Take your first node A. It has children B and C. A's index is 1, B and C has indices 2 and 3. So is there a pattern here?
The first child is always twice the index of the parent.
First child is always twice the index of the parent. And the second child is just right after that. So if you have node N, children are 2n and 2n plus 1. And if you have a node C, what's the index of its parent?
Would be the floor of F.
Yeah, it's just C over 2 taken as an integer, so round down if C was odd. So the main movement that we make in a heap, which is moving from a parent to a child and moving from a child to its parent, is really, really simple index arithmetic. To get to your children, double your own index and then add 1. And to get to your parent, just take your index and divide by 2. Really, really straightforward. Very fast. So we don't use pointers, we don't use mallocs, we just have a big array. Well, maybe we malloc the array, but we have a big array, we store our data in there sequentially, and we can move around by simple index arithmetic. Now the other thing we want to do is we want to identify the root. Well, where's the root always going to be? It's always at index 1, so there's no work to do for that. The other thing is sometimes we want to insert in the lowest row in the rightmost position. Well, that's always going to be at the end of the array. So as long as we have some variable like heap size, which tells us how many things are in the heap, if you want to add a new element to the heap, first thing you do is you increment heap size, you store your element at that location. And then your up heap is a matter of, you know, finding your parent, comparing it to both children, right? It's just a bunch of arithmetic expressions.
Is the heap size ever stored in the 0th element?
You could store it in the 0th element. That would be handy. And then if you want to heapify, right, if you're taking in data, I lost my heapification, there we go. if you're taking in data and you want to throw it into a heap shape, just fill it in sequentially in the array. And that lays it out from top to bottom, moving across each row. So this is like as simple as you could hope in terms of actually coding this. So heaps are useful. They're fun to code. It's a nice break from pointers and seg faults and things like that. And then if you want to delete, right, take the value at element 1, return that as the smallest in this case if it's a min heap. Take the element from heap size, copy that to element 1, decrement heap size. That moves your last element up to the root. And then start there and do your down heap. All right, any heap questions?
I assume you use a dynamic array.
So if you don't know how much data you have to begin with, that can be an issue, but yeah, you can malloc memory.
And when you're doing that, I assume it would be better to not realloc all in one. Just from like a user perspective, if you're the unlucky thousands customer or something, it takes forever. So do they have some way of spreading that out over time?
Yeah, there's different algorithms you could imagine. If you have no idea how much data you're getting, right, you make a best guess and pull your data in. If you can tell along the way, you know, how close you are to done inputting data, once your first one fills up, maybe you can do a better guess for mallocing a second chunk. Or maybe you just malloc a bunch of, you know, million element arrays and string them together when you're done. Managing large memory is its own subject in some ways. I mean, you could make this a million elements, or probably a power of 2, right? And have a collection of these. Maybe throw those in a linked list or something. And then have a way to, you know, maybe in location 0 you store the index of the next array and do some more math. So if you try to access an index beyond what's in the array, you can go modulo the size of the array to figure out how far through the array you are, and integer divided by the size of the array to find out the array number. And you're basically cobbling together a 2-dimensional array then. But I don't know if you would use a heap if you had an unknown, unlimited amount of data coming in to store. I'm not sure there'd be a case where you wanted to do that and actually just pull off the maxes or the mins. Well, I mean, there probably is, but I can't think of one.
Have we talked about dynamically creating arrays?
Malloc. So if you say how many numbers do you want to enter and the person says 5,000, then, you know, you just do something like integer array equals malloc number of elements times size of int. That's basically a dynamically created array.
I mean, adding on those cells.
Making an array bigger?
Yeah.
No, we haven't really talked about that. So there's functions you can call that will say extend the size of this chunk of memory, and it's basically reallocating. So it'll look for a chunk of memory that's bigger and copy stuff over from the old location. Or you can just malloc a bigger size and use memcopy, or just make a for loop and copy the contents over and then free the old array. But depending on your environment, your operating system, your language, and so on, there's different ways that are more or less efficient. Memcopy may be more efficient than doing a for loop, because some CPUs have hardware support for copying blocks of memory that you might circumvent by writing a for loop yourself. Cool. Any other questions, comments? you'll definitely see heaps on the final, along with AVL trees and lists and trees and sorts and stuff. All right, so one more sort. Radix sort. Radix sort is kind of quirky in a good way. So let's imagine we have 3-digit numbers. And we want to sort these, say, smallest to largest. And this wouldn't usually be something we do with numbers, but it would work better with words, maybe. But what we're going to do is we're going to treat these numbers as strings of characters. Okay? And we're going to sort digit by digit. So here's digit 0, digit 1, digit 2. And it's counterintuitive which end we start with. But I know the correct answer, so there's a good chance I'm going to get this wrong. Because I'm going to think the correct answer is counterintuitive. So let me see.
Would the last digit be counterintuitive?
I don't even know anymore. That's not a good approach for me, I guess. All right. I'm going to say start from D0. If this doesn't work, we'll do it the other way. Start from digit 0. And we're going to go through and we're going to sort based on that last digit. Okay. Since we only have a finite number of symbols here, we can actually do this without bubble sorting or merge sorting or anything. We can simply do the following. Let's move through and pick out everything that begins with a 0, everything that has a 0 in this last position, and let's add it to an output list. Okay, so I'll move through, there's nothing with a 0. Now I'll move through and find anything that has a 1, and I'll put that in our output. Look for the 2s, there's nothing that ends with a 2. Look for anything that ends with a 3, there's 1, which is 583. Look for their 4s, there's a 674, and so on. Nothing with a 5, there's a 476. There's a 477. 8s, there's a 278. And 9s, there's a 219. And continuing, there's a 999. Okay, as we're sorting by the smallest digit, it's really important that we don't change the order of anything in here if it has the same digit. Okay, this is where a bubble sort, for example, might not work for us. So making repeated passes and pulling things out that have the digit we're interested in works well for this. Okay, so we sorted by digit 0. Now we're going to sort by digit 1. So we're just going to look at this middle column. And we'll start with a 0, so there's a 101. Go on to the 2s, there's no 2s, no 3s, we'll find no 4s. Oh, there was a 1, 219. Okay, no 2s, 3s, 4s, 5s, or 6s, but there are some 7s. So we'll take the 674, the 476, the 477, the 278, There's one with an 8, that's 583. And there's one with a 9, that's 999. So now we do this once more, but we sort by the most significant digit. So there's no zeros, there's a 1, there's a 219 and a 278. There's no 3s, there's a few 4s, 476, 477. There's 1 5. There's 1 6. No 7s, no 8s, and there's a 9. And we're done, and there's your sorted list.
So why can't we start from the largest digit?
So, suppose we had numbers, numbers like that, right? So if you start with the largest digit, you'd get 109 and 217. We'd go on to this, we'd still get 109, 217, and then when you sort by this, we'd say 217, 109. All right, so to me, at least you feel counterintuitive to start from the smallest. I guess the intuition is the leftmost digit is most significant, and so that's the one that's going to determine the final order if everything else is the same. Does that process make sense? So this works really well for like strings of characters, right? So it's an interesting order of complexity to analyze. So suppose we have n numbers. Well, to move through and pick out all the numbers where this digit is a 0, that's an order n operation, right? And then to go through and pick out all the numbers where this is a 1, that's another order n. And pick out all the things that end with 2, that's another order n. We have to do that 10 times. So it looks like this first pass is an order 10 times n operation. And if we suppose that our largest number is 4 billion, that's a 32-bit number, so that's 10 digits. So we would have to do this 10 times. That's 100n. That's order n. So this looks like an order n sorting method, which we've kind of said we don't have. Right, usually the best we can do is n log n. Well, suppose we think about these numbers as being written in binary. So it's a string of 0s and 1s. So our numbers might look like this. And imagine we have n of these numbers, but they're 32 bits each. Well, sorting this by this least significant bit is pretty straightforward now. Simply go through, find all the things where this is a 0, copy that to your output array, and then take all the other ones where this bit is a 1, add those to the end of the output array. Right? That's 2n operations. And we have to do that 32 times, one for each bit. So that's order 64n, which again looks like order n. Super efficient. So is this better than merge sort, quick sort, these other n log n sorts?
It'd be really good for cars and stuff like that.
Yeah.
For neighborhoods.
But it's
Depends
a
on your
better.
data set too.
Say again?
Depends on your data set, I suppose, too.
Well, suppose you have a bunch of integers, bunch of integer data.
'Cause the more data you have, the more it's asymptotically approaching order n.
Mm-hmm.
So the bigger the data, the better it gets for it.
Yeah, it would seem that way. So is this better than a quick sort or merge sort, which is n log n? I mean, asymptotically it is, but what about practically?
It's a big constant, so.
It's a big
At some point,
constant.
they're gonna probably cross, but I'm not sure how big that is.
Suppose you have 4 billion numbers. I mean, that's all the integers we have in a 32-bit integer. There's only 4 billion possible values. So suppose you have an array with every possible integer in it that you want to sort. That's kind of worst case, right? Unless you're sorting stuff that has duplicates. Well, if n is equal to 2 to the 32, that's 4 billion. Log n is 32. So n log n is 32n. And this is going to be more like 64n, plus a lot of memory movement. So asymptotically, a radix sort looks like order n, but when you don't brush those constants away, asymptotically, right, this is actually on par with any of our other good sorts, and possibly worse. So again, that's the kind of analysis you get into in like an algorithms course. Yeah.
Are we gonna be doing stuff like that on the final?
You're going to see something involving sorts. So, no, but no, not asymptotic analysis. No. But you will be sorting stuff. All right, any other questions? All right, so I'm going to call this the end of material for the final exam. Okay, because I don't know how far we'll get from this point, and I don't know how this section and the other section will line up. I think the other section is going to take longer for SLP presentations because there's more people in there. But I want to talk about some other stuff that we'll be using in 223 and that you'll see later on. And in particular, stuff we didn't get to in 215, the first term, and that we may not get to this term. So let me talk about graphs. All right, so not on the exam, but still really good to know. So what is a graph? Well, draw a bunch of points and connect them in some way. There's a graph. And this graph could actually be a tree, right? If this is A, B, C, D, E, I could draw this differently as this, and now that looks like a tree. So the way that I write this on paper is not meaningful. Okay, what's meaningful is the collection of these points, which are called vertices, and the lines connecting them, which are called edges. And a graph can have things like this. So now I have an edge between B and E. Well, suddenly that's not a tree anymore, right? Because E has two parents. If this were a tree, it would have both D and B as a parent. Okay, so graphs are generalizations of things that trees are. Trees are a specific type of graph. We can have multiple connections between edges. So now we've got two edges connecting D and E. We can have pieces of graphs that aren't connected to other pieces. So this is all one graph containing 7 nodes and a number of edges. We can have weights associated with these. We can have directions associated. And graph theory is a very broad subject. There's lots of interesting work that goes on. There's lots of good theory associated with graphs. We're going to work more with the mechanics of graphs and thinking about how we can work with these things inside computer programs. And I want to talk about a few algorithms for doing work with graphs. So I don't want to get heavy on definitions, but I do want you to understand vertices and edges. Okay, vertices are basically the points. Edges are things that connect the vertices. We could have a vertex with no edges connecting it. That's just like an island. But you can't have an edge that doesn't connect stuff. You can't just have an edge hanging out there. But we could have something like this. So there's a single vertex I that's got an edge going to itself. And so what can we do with graphs? Well, we can represent lots of different information. So a common model is a map, right? We can think of these vertices as cities, for example, and edges as saying that there are airline trips possible from one city to another. And so you can fly from city A to B in 4 hours, and from D to B in 1 hour, and so on and so forth. So I'll make this a directed graph. So we can fly from E to B in 1 hour, and maybe from B we can fly back to E. But that takes 3 hours for some reason, jet stream difference. I don't know what's going on over here. Those are 2 cities you can fly between, but can't get there from anywhere else. This is probably some kind of like tourist thing. You can only fly from eye to eye. And maybe it takes an hour. And here's a city that has no air access at all. So we can use graphs to talk about networks. So here's a node called N, and here's an S1 and an S2 and an S3. And here's C1, C2, C3. So this could be a network graph for Netflix, right? So Netflix has access to 3 servers, S1, 2, and 3, and as a customer you have the potential to connect to any of those 3 servers, right? And so we can see that if, for example, S1 were to go down, if that vertex were to be removed from the graph, you still have connectivity from N to each of the customers. Right, but of course if N goes away, So maybe we want 2 Netflixes that can each transmit to these 3 servers. And if, a connection gets lost, if this edge goes away, you still have access to other servers. And maybe you can weight this graph by how expensive, either in terms of dollars or in terms of time, it is to transmit along each of these links. Maybe one of these links is very fast fiber and the other one is slower copper. And maybe you want these servers to be able to share information with each other. So you can make a graph for your network connectivity and you can ask questions about it, like what's the average length of time it takes to get from this point to that point? What's the worst case? How many edges can I remove and still ensure this level of connectivity? Okay, that's all good stuff in graph theory. So the layout on paper is not meaningful, right? That's just how it's being drawn. What's relevant are what are the vertices, what are the edges that connect those vertices. So if you want to represent a graph inside a computer, we need to store that connectivity information. And so there's a few ways to do that. Let me make a graph. So there's an arbitrary graph. So here's an idea. Make a linked list of vertices. So each node is a usual linked list node, and the data there is an identifier for the vertex, a letter in this case, as well as a sentinel for another linked list. And what I'm going to do is I'm going to build a linked list from each vertex showing every vertex that's connected to it. So A is connected to B, and it's also connected to D. And B is connected to A, and it's connected to C, and it's connected to E. And C is connected to B and F. D is connected to A and E. E is connected to a bunch of nodes D, A, and B, and F is connected to C. And so that's a connectivity list of lists. And it can grow because it's linked list. It's not bound by initial dimensions. But it may not be the most useful structure, but it's not bad. If you want to add a new vertex, we just add a new vertex at the end of the list here. And we list its children, and anything that it's connected to, we have to go through and add that new node. And if you want to remove a vertex, you simply remove it from the list and go through each of these and take out anything that refers to it. All right, here's a different way we can store this information. Make yourself a matrix. And let's just record in this matrix anytime that something is adjacent, connected by an edge to another vertex. So A, for example, is connected to B and D. So I'll just make this binary, right? And everything will be a 0 if we don't fill it in. B is connected to A and C and E. C is connected to B and F, and so on. Right, so fill in zeros everywhere else, and this lets us know what's connected to what. And if this is a weighted graph, instead of just storing a flag, we can store the actual weight. And if it's directed, and our weights are not negative, we could use, well, if it's directed, we can say this is, say, from this vertex to that vertex. If it's undirected, this is symmetric, about the diagonal, because if B is connected to G, G will be connected to B, and so on. And so an adjacency matrix is a useful way to store connectivity information. And it lets us do some calculations. For example, if we add up each row, we get a 3, a 2, a 2, a 2, a 4, a 1, and a 1. This tells us how many edges each vertex is connected to. For example, that 4 next to E tells us that E is connected to 1, 2, 3, 4 edges. And some of the algorithms I want to talk about need us to understand what this connectivity looks like. Right? How many edges a vertex is connected to, or is there a path from one vertex to another? And if there's weights, what's the weight of that path? If we had weights in here and we wanted to find the shortest distance from B to another node, we would simply find the minimum of these values. And if it's right here, then we know that B is the shortest distance. All right, so when we come back to this, which will probably be Wednesday or Thursday, I want to look at algorithms we can use for analyzing graphs, doing things like finding paths from one node to another that minimize total distance. Okay, so we'll play with that next time after presentations. All right, so SLPs tomorrow, and we'll go from there.